Hello there, Year 9 and 10. Welcome back to another online lesson from St Leonard's Academy in physics. I hope you enjoyed last week's lesson. Last week we did CP3 forces. This week we're going to look at CP4, which is a topic about waves, a really fundamental part of physics. What are waves? What are the different types of wave? What are transverse waves versus longitudinal waves? And a little bit of exam technique. Next week, we're going to move on to CP5, which is electromagnetic waves. And after we finish that, we will have touched on all of the topics in paper 1 for physics. So I know that last week's lesson was a little bit long, so I've put a lot less material in this one, so it should take a lot less than 1 hour. The equipment you'll need, as always, is a pen, paper, and ideally a quiet, clear workspace. You won't need any calculator for this lesson, and I can also say there are going to be lots of GIFs or GIFs. I don't know how to pronounce it, so you can laugh at me if I've got it wrong. If you haven't got a paper and a pen and a quiet workspace, then please can you pause the video and go and get one now. Okay, I'll assume that you've got them. Let's move on. Just very quickly, work expectations for lockdown. You've seen it, it's the start of every one of our online lessons here. We would like you to try and complete 3 hours of science work per week. And that can be revision booklets we've given you. It can be online lessons such as this one, or it can be your own work. For example, revision using BBC Bitesize or Oak National Academy. So, without further ado, the LQ for this week. We don't really have a starter as such, just an LQ. If a tree falls in the forest with no one to hear, does it make a sound? Part philosophy, part physics. I'll leave you with that one. Hopefully you'll have an answer by the end of the lesson. Maybe, even if there's no person around, the badgers might hear it. Okay, let's just go straight in. We don't have a starter because we're just going to go straight in. We're looking at waves. What is a wave? Let's see if we can get some kind of definition of a wave. Let's see if we can build a definition up. Okay, so here we have a water wave, or a GIF of a water wave, or a GIF of a water wave. Looks like the waves coming towards us, and you might assume that the water's coming towards us as well. If we look at the wave side on and we highlight some of the particles in that wave, what we can see is that the particles are moving. I don't know, frozen. There we go. The particles, the wave is moving forwards, but the particles in the wave aren't actually moving forwards. They're moving in a circular motion, up and down, up and down. You could say that the particles are vibrating or oscillating, but the particles aren't themselves moving forwards with the wave. Okay, and that's a really key part of all waves. All right, now I understand that if you think of a wave at the beach, it looks like it comes forward and crashes up onto the beach. That is because as the seabed gets very shallow, the bottom of the wave kind of gets pulled backwards and the wave does crash forwards. However, if we're out to sea, what we can see is the waves act like this and the particles oscillate or vibrate, but they don't actually move forwards and bulk themselves with the wave. Okay, let's have a look at another example of a wave. A sound wave. What is a sound wave? I don't know if you've ever considered that. Here is a GIF of a speaker. Now what we can see is how the speaker creates sound wave is it vibrates forwards and backwards. Now, if we see that vibration in the air molecules around the speaker, we can see that the vibration is carried in the air molecules around the speaker. We can see it traveling forwards. A wave of sound energy, you can see it labeled here, wave, travels forward. And it's a compression. As the speaker vibrates, it compresses and then expands the air. So we can think of the sound wave as a traveling compression of air, of the air molecules. So we can see the waves moving forwards. Now, let's have a look at an individual particle. If you look at a particle in the sound wave, so this would be an air molecule in this case. Look at it closely and you can see that the particle doesn't move forwards with the wave. In fact, it moves backwards and forwards. It vibrates. So the sound wave is transferring energy from the speaker outwards. It's not transferring air from the speaker outwards. So we could say that the sound wave is transferring energy, but not mass. Okay, and what we mean by that is that the air molecules themselves aren't moving forwards with the wave, they just vibrate about one position. So we could say waves transfer energy and information, but not matter, not the actual air itself. Okay, time for you guys to do something. Here are 3 other kinds of wave, 3 more GIFs, and 3 more kinds of waves. I would like you to try to guess what are the 3 waves. You can pause the video and have a guess. 1, 2, 3, and then we'll go through. Pause the video now. Okay, let's have a look. So, did you get it right? The first one is an electromagnetic wave, for example, visible light. So it's a glow stick, it's giving off visible light. Visible light is one part of the electromagnetic spectrum. So if you put light, then you're correct, give yourself the mark. But light is just one part of the electromagnetic spectrum. Okay? Second one is in Dave. I hope you all got that. Mexican waves. In the audience, stand up and sit down. They move, think of them like a particle. They move up and down. And yet the wave moves around the hole. So you could say in the Mexican wave, the people are moving at right angles to the direction of the wave propagation, or the wave travel, sorry. And finally, the third one is a seismic wave, or if you wrote earthquake, that's also correct. But to be more precise, we can say a seismic wave. Seismic wave is a wave that travels through the earth, okay? And they happen as a result of faults, or sometimes huge explosions which we set off underground. And there are actually different kinds of seismic wave, as I've put there, P and S. We'll worry about those in a bit. Okay, so you might not think of light as similar to a water wave. You might not think of it as a traveling kind of oscillation or a traveling vibration. However, if we kind of zoom in on one ray of light, one photon, we might see something like this. Okay, this is a model of a light wave showing the oscillation in the magnetic and electric fields. So an electromagnetic wave, light being one of them, is in fact an oscillation, a vibration in the magnetic and electric background fields of the Earth or space. Okay? And what you might notice that if the wave is moving forwards this way, the vibration of the electric field, which is E, is at right angles to the movement of the wave. And the vibration of the magnetic field, that's B, is also at right angles to the movement of the wave. So they vibrate this way or this way, up and down, but the wave moves forwards. So think about that when you think of what a wave might be. Mexican wave, obviously we have movement of particles up and down, and movement of the wave, which is along. An earthquake, just for those who don't know what an earthquake is, don't worry, we haven't done it in science before, you might have done it in geography, is an earthquake happens when the Earth's crust is pulled apart at a fault line. This is an example of one kind of fault called a normal fault. Now, as the Earth's crust is pulled apart, what you can see is there's a huge release of energy, and that energy travels out through the Earth as a seismic wave. There are, in fact, different kinds of seismic wave, as we said. We can have P waves. The two we need to worry about. There are even more than this, incredibly. But the two that we have to worry about for GCSE are called P waves and S waves. So these are both seismic waves. But if you notice the P wave, the particle, so you could say this is a part of the Earth, the particle moves forwards and backwards in the same direction as the wave moves. Direction of propagation just means the direction that the wave moves. And in our S wave, the bit of the Earth moves up and down, so at right angles to the direction of the wave. So two different kinds of seismic wave. Okay, so what is a wave? You can go back and look at those examples of waves. I would like you to try to come up with your own definition of a wave. I've got 3 different points which I'm going to bring up, but I'd like to see if you can get them yourself. So pause the video and try to write your own definition of a wave. Okay, I'm going to rely on you for having paused the video. We're now going to move on. What is a wave? What is a wave? A definition. Okay, it's easier to think of what a wave does. Waves transfer energy or information, but not matter. So when we think of our water wave or our sound wave, we think the particles themselves vibrate. They move up and down, round and round, backwards and forwards, but they don't actually move forwards as whole themselves. And that's what we mean by this. Waves transfer energy or information, but not matter. Waves, if we think back to our last lesson on energy, waves are one of the ways in which energy may be transferred between stores. So between kinetic energy and thermal energy, for example. Think of the sun, it's very hot, it's got a lot of thermal energy, and it radiates out electromagnetic waves out into space, some of which hit the Earth, or we receive the electromagnetic waves, which then, for example, plants can change into chemical potential energy in their leaves for photosynthesis. So we can transfer energy between stores. Waves can be described as vibrations or oscillations. Oscillation is another word for vibration. About a rest position. So that might seem a bit confusing, but if you take one particle, for example, in our sound wave, and you have a speaker which is vibrating, our air molecule will vibrate or oscillate about a rest position. Its rest position could be this, and it vibrates like this. It comes back to its rest position, which will be in the middle. So if you didn't get any of those 3, then please include that in your definition for a wave. Okay, 2 kinds of waves that we need to worry about. So these are two kinds of wave motion. So we have all the different types of wave that we saw. Now we're going to look at 2 different kinds of wave motion. These are really, really critical. It's important for you to understand them. 2 types we need to know for GCSE. Let's get a slinky out. So slinkies are really fantastic for showing different wave motion because we can quite easily show both transverse and longitudinal. I don't have an actual slinky. I have a GIF of a slinky instead. Here we go. So a slinky is a big spring, if you don't know what I'm talking about with a spring. If we pull the slinky out, if we pull out the slinky across the table, for example, and I get my hand and I move it, so I pull the slinky out this way. If I move my hand up and down, I can create a transverse wave like this. If I move my hand forwards and backwards on the slinky, I can create a longitudinal wave. Remember, all waves transfer energy, but not matter. So what do we mean by this in this case? Have a look at one part of the slinky and see how it moves. In our transverse wave, if we look at this bit, it moves up and down, up and down. The wave moves along, but the spring moves up and down. If we look at our longitudinal wave, on the other hand, the wave moves along, but the particles, the little bit of the spring, moves backwards and forwards, backwards and forwards. It's a bit hard to see in that GIF. But here we go. We've got the direction of wave travel is this direction. In our transverse wave, the spring is vibrating like this. We could say at right angles to the direction of wave travel. In our longitudinal wave, however, the spring is vibrating parallel to the direction of wave travel. You may see propagation used instead of wave travel, but we can think of it just as the direction of wave travel. So if we're going to define these two, transverse and longitudinal, you could say a transverse wave, vibrations are at right angles to the direction of wave travel. Whereas longitudinal waves, the vibrations are parallel to the direction of wave travel. Can you please pause the video and write down the definition for a transverse and a longitudinal wave? Leave a bit of space underneath for some examples of different transverse and longitudinal waves. You can pause the video now. Okay, just a little tip for remembering which is which. How I like to think of it is, if we think of transverse, it's got lots of S's in it. S, 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 S. And I think transverse, and I think across. Which has two S's in it. Transverse waves, the motion is across the direction of wave travel. The wave's going this way, and the vibration is across the direction of wave travel. It's like along, long, along, and the vibration is along the direction of wave travel. Wave travels this way, for example, and the direction of vibration is along the direction of wave travel. Okay, now time for you to do something. I want you to transverse or longitudinal. We're going to see the same waves that we just had, and I want you to say whether they're transverse and longitudinal. Water wave, transverse or longitudinal. Confusing, I know, because we've got them going in a circle. However, we think of water waves as being, give it a guess, they're transverse waves. We think of the particle motion as being up and down across the motion of wave travel. Water waves are transverse. Sound waves, transverse or longitudinal? Are the particles moving at right angles to or parallel to or along the direction of wave travel? The answer is longitudinal. Electromagnetic waves. This is our light wave. Is this motion, is the oscillation or the vibration in the fields transverse or longitudinal? Pause the video. They're transverse. How about a Mexican wave? Are the particles moving at right angles? If our wave's going this way, are the particles moving along, longitudinal, or across, transverse? The answer is the Mexican wave is a transverse wave. And finally, we have our earthquake. Look at that. Look at the guy try and walk. That shows just how much the earth is vibrating. This is not a camera trick. This is a real to suffer from earthquakes, but other countries have terrible earthquakes and they can lead to huge losses of life. Earthquake, do you think it's transverse or longitudinal? Tough one. Now this is tough. And as I said, or as I alluded to earlier, in fact, there are both transverse and longitudinal seismic waves. You need to remember that the S wave, and you can think of it as an S like, again, like transverse, S across, S wave is a transverse wave. A P wave, another kind of seismic wave, is longitudinal. The vibration is along the direction of propagation, or the direction that the wave is moving. So if we have an earthquake, it will produce both of these kinds of waves, transverse and longitudinal. P wave and S wave. P wave, I remember P wave by pressure wave. If we think of a pressure wave, it's the same as a sound wave, and it moves along the direction of wave propagation. Okay, we're almost finished this lesson. Surprise, surprise. It's a short one, I promised. As I promised, it's short. I'd like you to bring it all together and draw a table out on your paper. I want you to have 2 columns, transverse wave, or 3 columns rather, a transverse wave and a longitudinal wave. I'd like you to define a transverse wave and a longitudinal wave. I would like you to draw a diagram of a transverse wave and a longitudinal wave. Go back to the slide with the slinky and draw that out. If you don't know what to draw, draw that. Examples of both transverse and longitudinal. Now, don't worry if you don't know these. Just flick back to the earlier slides. All of these are gone through on the slides we've just done. Okay, so you should be able to complete this table. Now, for the extension task, if you're a higher or a triple student, what do we call the different parts of a transverse and a longitudinal wave? This is a revision lesson, so you should have seen this before. There are 2 parts. I mean, the top part and the bottom part of the transverse wave, and the compressed part and the expanded part of the longitudinal wave. You might need to research it, in which case research it, find it out. Okay, can you pause the video now and fill in the table? I'm going to rely on you having paused the video, because now we're going to go through the answers. If you didn't get it, don't worry. Here are the answers. I would like you to fill in the table with any of the bits that you didn't get. Okay, so definition for transverse. The vibrations are at right angles to the direction of travel. So here we go, and here's the diagram. Okay, the wave is traveling this way, forwards, and the vibrations of the wave are up and down. They are at right angles to the direction of travel. Examples of transverse waves: light and other electromagnetic waves, water waves, and seismic S waves. Longitudinal waves. Oh, and what do we call the different parts of the wave? We call it a peak and a trough. This is a peak and this is a trough. Peak is the top, trough is the bottom. Longitudinal waves then. Definition: the vibrations are along the same direction as the direction of travel. They are parallel to the direction of travel. In our diagram, you should have drawn something like this, with areas of a spring or air molecules. If you did air molecules, that's fair, that's fine as well, where the spring is closer together, like here. We call those compressions, and areas where it's slightly further apart. These travel forwards. The parts of the spring itself vibrate backwards and forwards, vibrate or oscillate backwards and forwards. The bits where the spring is close together we call a compression, and the bits where it's far apart, this is for the extension task, we call a rarefaction. That's a very strange word, you just have to learn it. Rarefaction. R-A-R-E-F-A-C-T-I-O-N. It's spelt out here. I know I'm covering it up here. Okay, I hope you've got all that information down because you will need it for our exit ticket, which here we are. Don't get stuck in. Do not start just yet. We're going to do a little bit of exam technique first. Here's an example of a question you might get at GCSE. The question for you is, what is the question actually asking? Okay, so let's go through it. Matthew and Rob enjoy fishing at sea. They have hired a boat and are bobbing up and down pleasantly whilst having a discussion about the relative merits of carp. Note that's carp, not another word which looks like carp. Carp is a type of fish, which fishermen like to fish. Compare water waves to sound waves. So they're bobbing up and down because of the water waves, and they're talking. They're using sound waves to communicate. Which bits of the question are important for us to know, are important for us to concentrate on? It is just the last sentence. Okay? Compare water waves and sound waves. The question of even a long 6-mark question of a physics paper, the question will always be on a new line at the end of the question. You need to sift through, you need to go through all of the useless, pointless information included in the question and find what's most important. And the question sentence will be at the end on a new line. So in this case, compare, that's a question word, which means take two different things and say how they are the same and how they are different. That's what compare means. So compare water waves to sound waves. In what ways are water waves the same as sound waves? And in what way are they different from sound waves? Because I'm very generous, I'm going to give you even more help. Okay? How to go about a compare question. Oh, not moving on. Okay, so our question was compare water waves to sound waves. How I might do this, if I had done this many times in practice, I might just go straight ahead. But if I was a bit stuck, what I might do is make a Venn diagram, which is going to help me answer the question. So a Venn diagram is where we draw circles like this with water waves, sound waves, and both. So we can see things that water waves are, things that sound waves are, and things that both water and sound are. Now, if you have a good idea how to get started on the question, you can, of course, just go straight on and get stuck in. If, however, you are still struggling a little bit, then stay on the presentation, and I'm going to give you even more help. Okay? So, here's my Venn diagram. Water waves, sound waves, both. I'm going to give you a bunch of ideas about waves, both water waves and sound waves, and both. I'm not going to put them in the right box, so you'll have to put them in the right box, and then you can use them to help you write your answer for the 6-mark question. Remember, you need 6 points. So, transverse energy has a wavelength and an amplitude. We didn't go over that in this lesson, so don't worry about that if you don't know what that one means. There's enough of the rest. Particles vibrate, travel in water or liquid, both waves, both move, travels in peaks and troughs, travels in compressions and rarefactions. That one says can be reflected, can be refracted. These are purple, so these are for higher or triple students. Don't worry about these if you're combined and lower. Transverse matter, question mark. Vibration is at right angles to the wave travel. Vibration is parallel to the wave travel and can travel in solid, liquid, or gas. Whoops. Okay, so draw your Venn diagram and put these into whichever section of the Venn diagram they fit in. Then, when you go to answer your 6-mark question, compare and contrast, you will have a huge number of points. You just need to put those into sentence form. So, for example, here's our question again. Compare water waves to sound waves. Your answer could start, a water wave is a transverse wave. That means that the vibrations of the water move at right angles to the direction of wave motion. You could also start with both water waves and sound waves are waves. This means that they transfer energy and information, but not mass. Water waves, however, are different because, and then something that just water waves are. Okay, it's a 6-mark question, so you're looking for 6 separate points. Submit your answers and write in full sentences and pay attention to spelling and grammar. You cannot get a full 6 marks if you don't have correct spelling and grammar and full sentences. If this is too easy, or if you're a higher or triple student, then stay on for the extension task. Otherwise, you can finish with this 6-mark question. Submit your answers to showbie.com, class code HZ9N9, due Tuesday the 30th of June at 5 minutes past 12 in the afternoon. Okay, and finally the extension task. This might look completely bananas, like you've never seen anything like it before, but you don't need to have seen anything like this before. Look at our question, extension task. It's another 6-mark question, but you don't need to do this in full sentences. Look at the GIF of refraction of white light through a glass prism and describe what you see. 6 marks. This is practicing an essential skill for a scientist, which is describing something that you are looking at. You don't need to have prior knowledge to describe what you're looking at. Okay, you've got all the information that you need here. So to describe, it's simply say what you see. And there are at least 6 things that I can see in this diagram which are interesting. Okay, this GIF. So see if you can get all 6 or even more. Bullet points, absolutely fine. You can also write it in full sentences. And same as the previous question, submit your answers to showbie.com, class code HZ9N9, due Tuesday the 30th of June, 12:05 p.m. Thank you very much for joining me for another lesson. Looking forward to seeing you next week for our final theory lesson before we go to an end of term test, which I think you'll enjoy. Hopefully you'll enjoy. See ya.